And there it is. And it'll fit on just like this. Has to be silver soldered or brazed on. I'll clean all the corrosion off this tubing first. Now, one thing I didn't explain before I parted this off, how I actually made this hole. I faced the end of the work. I center drilled just as deep as the pilot on the center drill. Then I put an end mill into the drill chuck and fed it in again to the depth of what amounted to the pilot here. There's still a little bit of that showing. That gave me a flat-bottomed hole in which to start boring, because you can't really plunge bore. You got to have some place to start. So that's what I did. That doesn't work real great, but it got the job done. There's a lot of movement of the tailstock. You know, it just doesn't have the rigidity really to hold an end mill, but it worked for this job. Well, it's a new day, and now I want to tackle the problem here of putting the end cap on. And I brought the displacer up to the maximum position, and when I measured it, I determined that there is 5/16 of an inch altogether. So I want to leave about 1/8 of an inch at the end, so I have determined that I need to take 3/16 off. And I marked that all the way around. Now I'm going to grind that off with the Dremel cutoff tool, clean it up, and make it ready for silver soldering. Okay, I've sawed this off the length and I brightened it up real good and got all the corrosion off near the end. And now I'm ready to flux it. There's my flux all ready to go, and I'm going to use Harris Safety Silv 45 using my acetylene torch, not oxyacetylene, it's just straight acetylene. And I did have to take the project apart, because if I left the displacer in there, it probably would get melted during the silver soldering operation. So now I'm going to set it up in the vise and silver solder that off camera. I've silver soldered the end cap on, and then I reassembled the thing and I checked for leaks. And the way I did that is I just took a common cork and I corked up that side and then sucked on this with my mouth like you would suck on a Coke bottle, you know, to form a vacuum. And a vacuum was formed and held reasonably well, and that proofed it. Now there would be minor leakage right around there. That's why the vacuum probably would not hold. No matter how good the fit, you know, there's going to be a little bit of leakage. It's right there. And also I do not have any gasket or a sealant on this yet, so I will do that later on. But at this point, spins over, everything clears. I know I have minimum space when the displacer goes to the far end here, and you know, only about 1/16 on this end. And now I'm ready to turn my attention to this side and make the piston and the connecting rod, and have maybe 2 hours worth of work left, and the job is done. I took the piston out of the finished engine, and this is what it looks like along with its connecting rod, and it's nothing more than cold rolled steel. And I put a little groove in there originally. I don't know if that's necessary. I cannot use oil. I need to use graphite. Oil tends to gum up because of the heat and then causes resistance. And it's hollowed out to reduce the weight, kind of like a real piston. And then there's a cross pin there. I guess you'd call it the wrist pin or the piston pin. And a couple spacers there to keep the connecting rod in the middle. And that's what I'm going to tackle right now, but the thing is, this has to be a very good fit. Like I told you, pop a top or two. This is the piston so far. It's 3/4 inch mild steel. I already put it in the lathe and drilled a hole, and then I ran a 9/16 end mill in there, 1/2 inch deep, so I have a flat bottomed hole. Now I'm going to put it into my Heinrich cross hole drilling jig, and I'll just slide it right in there, and I'll look down the bore with my little flashlight until I see the cross line that I already have laid out. Lock it and drill that hole through. That way I got a cross hole that is centered and really going through the center and not going off to the side. Then I'll put it back in the lathe and turn it to diameter, polish it, and cut it off. I drilled the cross hole 1/8 inch diameter successfully. I was going to make it 3/32, but I don't have a drill bushing that small. So 1/8 inch is the size of the wrist pin. It's important to remember that in working with a small piece like this, you really don't want to cut it off to length yet. This way you got a handle, you got something to hold on to, and it's something to chuck it by. The very last thing I will do is cut it off to length. At the last minute, I decided I'm going to grind the final finish and the final diameter on the piston for this little engine so I can accurately control the finish and the diameter. So I've got the little do-more grinder set up here. The machine is draped. Now my reverse switch isn't working, so I'm going to be turning the lathe in the normal forward direction, but it should really be in the reverse for best results. But I just dressed the wheel, and now I'm ready to grind. There's only a few thousandths to take off. Here's a little of the grinding. Boy, does that put a finish on it. About one more pass and I'll have it. Now when I do tool post grinding like this, I have the compound set at an angle here, and I do my feeding with the compound, so rather than the cross slide. So I have a little more control over it, the depth of the cut. I want to get this within a 1/2 thousandth. And there it is. Very nice fit. So I'm done. All I need to do is part it off and install it. The piston is complete. I've got a little brass wrist pin in there. It's 1/8 inch brazing rod is what it is. And I've roughed out the connecting rod. Now notice I put a cork temporarily on the other end here, and I know it's the wrong end, but I got a little more room to work here, so I put a couple drops of oil on that. And now listen to this, see if you can hear the pop. If you don't get that kind of popping noise, it isn't going to run. And I could feel the resistance as I pulled it out. I could feel the suction. Now I'm going to determine the length of this and drill the other hole and fasten it onto the crank over here. I've got a nice little selection here of brass, and I know it's tarnished and everything. These were kick plates off of an old door at the high school, and I sheared these several years ago into various width strips, and it's just perfect for this model making because it's nice and soft, easy to work with. It is distorted a little bit and twisted, so I have to straighten it. The Pexto shear tends to twist the metal as it comes off. Also, I have quite a large selection, much more than this, of various size brass tube, small rod in brass and steel and copper, and just about everything I could need. And if I need any more, then I go down to the hardware store and I get it, and I just keep it in here, and it's so handy. Now when you cut brass, it doesn't cut all that well, and in the smaller sizes with tubes, like tubing, use a jeweler's saw, something like this. Now I need to put a little bit finer blade in there, but a jeweler's saw cuts it real nice. Well, I finally got it running, and some of the things that I've done here are temporary. Like I still have a cork in here, and tomorrow when this cools down I'm going to go ahead and put the other plug in there and put it in with Loctite. I had to make a few other adjustments and minor improvements, and you're usually going to have to do that when you make a model, especially when it's like a prototype or you've only made a few of them. There's always improvements to make, and have to make sure there's no binding or any extra friction, but it runs pretty nice now. So let me stop it here and show you a few other things that I did. Using this tubing, 536 OD brass tubing, 1/8 inch ID, I made little bushings for this pivot point and the one on the other side also. That just gives a better bearing surface, and then we know that the screw isn't going to wear out the connecting rod. I took Permatex number 2, I think it's number 2, yeah, number 2, the non-hardening, and I sealed this surface here, and checked a few other alignments, and that's about it, and then it ran. I trimmed this little pin to length. I changed the end play here in this main shaft so that there was just a little bit of end play, but not too much, and that everything runs free. Now I'm going to Loctite this piece in place. I've already cleaned it with brake cleaner inside here and outside of this, so we'll use a little of this. Won't take much, and you don't ever want to get extra on there that might get into the piston. And as I put it in, I twist a little bit, and that'll spread it. And I'm not going to go, I'm just going to leave a little bit exposed so you got that extra surface. That's just for appearance. And now I'm going to bed. Good night all, I'll see you in the morning. Good morning, it's a new day and I'm wrapping up this project. I'm just going to talk a little bit about it and run it again, and then that completes this rather lengthy video. Remember, this is a heat engine. This principle here was invented by Robert Stirling in, I believe, Scotland a long time ago. And a heat engine is rather inefficient. Most of the heat is just being wasted. I don't know what the efficiency is, but it isn't very much. Also, it doesn't produce much power. And they have some practical uses for Stirling engines, but mainly it's a curiosity. And I do like to build them, and I've built a lot of different ones. And they may appear in many different configurations, but you always have a hot side and a cold side. That is a displacer side and a power side. Now I Loctited this in, so that's done. That's done for good. I brightened up the brass a little bit. I put a decent set screw in here. I had to retap that, so I had a 632 set screw. I do not have a 540 set screw, so that's why I changed that. I also had to do a little milling here to provide some more clearance. I did that off camera. I've got a little bit too much shaft sticking out there. I may have to remove that if there's any interference. We want no interference, no friction. But basically the engine is done, other than plugging these holes. I probably will not paint it. I'm not too interested in decorating or painting at this point in my life. Permatex number 2 non-hardening is the sealer that I used right here. Silicone's alright too, but it has to stand up to a little bit of heat, and the Permatex certainly will. Now remember, you can go to these videos of mine, so go to tubalcain videos and search Stirling hot air engines and principles of a Stirling hot air engine. That tells you how they run. But real briefly here, we have heat right here. We've got a displacer that's moving back and forth, and it's moving the hot air from this end down to the cold end. And when that happens, we have expansion and contraction. and that is translated over onto this power piston side. Remember, there's a hole in here, and causes a minor pressure at one point and minor suction at the other point. So there's both pressure and suction that is moving the power piston. When you build your Stirling engine, remember that it's extremely important to have good workmanship. That is, there can be absolutely no binding, no friction. I mean, you're going to have enough friction the way it is, but no extra friction such as in the rod here or in any of the other little parts of the bearings, or any more friction than necessary in the piston, or the engine will not produce enough power to even overcome all those internal frictions, and it will not run, and it'll be very discouraging for you. So any little errors that you might make in machining or constructing this thing will catch up to you at the time of reckoning, and the time of reckoning is when you light the fuel. You can use any kind of fuel. I've been using the solid S-bit fuel lately simply because there's very little room here to put a sterno or any other kind of heat source. So I have used propane and all kinds of other fuels too, but this serves me well because just lay this on a piece of steel and there's not a whole lot of room here to make that heat. And you shouldn't need an awful lot of heat. That is, if you have to come in there with your propane torch to get it to run, you know, that's probably more heat than what you need. And any source of fuel is okay. You know, it can be an old pair of smelly socks, or whatever is convenient for you to use. I also use alcohol sometimes. It works real nice, but I think the solid fuel is the least messy. One thing I believe that I failed to mention, and that is that Stirling engines have to be timed. That is, the orientation between the displacer and the piston is important, and they are 90 degrees out of phase. So when you look at the displacer, I'm all the way in, and the power piston has to be 90 degrees off of that, or 90 degrees out of phase. So this is in the down position, whereas over on this side the crank is in that position. Now if you want to run it in the reverse direction, you can reverse a Stirling engine simply by reversing this. So I could loosen the set screw in this crank and move this screw to the top position, and then it would run in the reverse direction of whatever it is running now. A Stirling cycle engine is a closed system. That is, the gas that is in here, and it's just atmospheric air, but it could be pressurized gas if we had a way of doing that. Helium works good. But there must be no leaks up here, no leaks back here, no leak here, but the reality is there probably is a minor leak here. I plugged this so there's no leak. I plugged the end and even used Loctite so that there's no leak. However, we know that some of the gas would be escaping around the piston because the fit has to be loose enough so there's no friction. So I'm sure there's a loss there. But in general, we want a sealed system, and remember that this side is connected with this side with a hole. On some of my engines I use tubing. It doesn't have to be a hole. It could be a piece of copper tubing or even plastic tubing going from here over to here. And it does not matter on this side where the hole is. The hole could enter this this hot side here or down here, and that isn't very critical at all. I'm just about ready to fire it up again. Now this time I'm going to use these Mammoth fuel tablets. They're slightly larger in size, so they give off a little bit more heat. However, I noticed they produce a heck of a lot more ash than the S-bit, but so be it. But while I let this come up to heat, let me talk a little bit about the dissipation of heat. And you know, these engines take 2 or 3 minutes to warm up. Anyway, as this end gets hot, the heat does get conducted down to this end, and that's undesirable but unavoidable. Now I did make one time with a copper tube, and it was a total failure because it just sucks the heat away so quickly and back into the engine. That's no good at all. Some engines need to have a cooling system, and I have made engines that had fins on them or a little fan, and I've made several water-cooled ones. I think they're on YouTube also. But as this end gets hot and the heat tends to equalize, that is, it gets almost as hot down here as it is here, and then they'll stop running, and that's not good. But the only cooling system on this engine really is that the heat does get conducted throughout the engine, and even the base gets warm, and then the heat radiates off of that. So the heat gets conducted into every inch of this engine, but it is not desirable. And it's not quite ready to go. We'll let that warm up and then let it run. How do we know when the engine is hot enough? Well, when it will run, then we know it's hot enough. But if it's just trying to run a little bit and doesn't continue to run, then the heat hasn't quite built up, and now it is hot enough. Now notice this, that it absolutely will not run in the opposite direction. You can actually feel resistance to that. But very quickly will run. Yep. And you'll determine exactly where the hot spot is on your displacer tube there. You don't want the flame too far down toward the engine. You want it out near the end. Already I can feel quite a bit of heat here. It's too hot to touch. And a little bit of warmth here as the heat gets conducted. Aluminum being an excellent conductor of heat. She's running pretty nicely now, and one little improvement that I did make after I got it running is I shortened the stroke by about 1/8 of an inch. Or should I say, I shortened the throw about 1/8 of an inch, which is almost 1/4 inch altogether in the throw. And there she goes. Pretty smooth running little engine. I don't know what the RPM is. You know, they more or less run at whatever speed they run, but some of them will run a little faster with more heat. But I like this slower speed because they don't vibrate, they don't walk around on you, and they're just kind of fun to watch. Well, there it is, man. A pair of them running in tandem with a common fuel source. I added one extra little fuel block to that so that it could feed both of them. And the new one seems to run about as well as the other one. I hope you enjoyed this video, man. I had fun making this engine. Remember, no castings, no plans available, but go ahead and copy this if you want. This is tubalcain signing out, saying watch my many other videos, and so long for today.